Hello guys, welcome back to the class. So remember in the previous class we discussed the false position method or the regular falsy method. So these methods were very similar to the bisection method in general because they use a line. You remember that the bisection was using a line actually divided into pieces with the same dimension. In this case, the false position method is pretty much like that. We have to select an interval A and B, and we have to make sure that the interval contains one root. To make sure of that, we have to actually evaluate the function in the interval and then multiply the results, and this result has to be less than 0. Okay, so defining that the C point, which is actually the point of the next iteration, at the second iteration or the first iteration, as you want to, do it, could be you could start from 0 and you can start from from 1 if you want. So, but in general, this is the formula that we use to solve any equation using the false position method. Okay, so and remember A and B are always the neighborhood. We already saw this. I'm just reviewing and making sure that you understand what I want you to do for the assignment number 6. So also I gave you a pseudocode that basically actually explained the method of false position. So remember that we have to give an interval A and B. We have to verify it by multiplying the functions evaluating the interval, and then they have to be less than 0. So we only need a for loop, we need the equation, and if conditional, where you evaluate the function in C. If this function is equal to 0, so you have to stop, and then C is going to be the root. If not, you just have to identify where the root is. If the root is actually in the side of between A and C, so you just have to actually rename B equal to C. Otherwise, you have to rename A equal to C. So, and then you just actually run the iterations until you get this condition. Remember that this condition doesn't have to be necessarily equal to 0. It could be equal to certain value that you selected, for example, 0.00001 or 0.1 to the power minus 6, something like that. This is your limiting error. Of course, try to be actually accurate. I don't say that this is equal to 0.01 because that's a very low limiting error, a very high actually limiting error. So, but in general, so the assignment was to actually code this one. You can use MATLAB, you can use Octave, you can use even R or an equivalent. You don't have, Excel is not allowed, so don't use Excel. You have to use MATLAB, Octave, or R, okay? And then you have to solve the four examples that we solved in the previous class using the secant method, okay? That's your assignment number 7 for you. So just make sure that you turn it in on time. So let's move to another method or to another modification of the secant method. The Miller's method is actually a generalization of the secant method. If you remember, the secant method uses actually 2 points that intersect actually the x-axis to obtain the solution. Miller's method now uses 3 points. So in general, this actually draws a parabola. And the parabola is equal to y equal to px in general, okay? This parabola will intersect the x-axis. And the parabola generally will intersect the axis in between, well, could be 0 or 2 points, right? So at least of them have to intersect the x-axis in 2 points. So if there are 2 intersection points, so we are going to select the one that is nearest to the last point, x2, and it's going to be name it to be x3, right? So in general, remember that when we iterate, the initial condition was equal to x0, x1, x2. In the second iteration, we will have x1, x2, and x3. That's why I'm saying that the one that is nearest to the last point, x2, will be chosen to be x3. So it's just a matter of using a simple quadratic formula to determine the two possibilities. And then we are going to be, by iterating, we're going to be very close to the intersection of the x-axis. However, if we have the first condition when you intersect the parabola with 0 or 1 points, so that's going to be a problem, because if you do this, you are going to obtain complex numbers in the solution. And we don't want to, we can go to complex numbers, but in general, for this type of equations, such as algebraic and transcendentals, we want to keep it simple. That's why I'm saying that in general, the Mueller's method is good as long as intersects 2 points of the x-axis. Okay, so that's important. So this condition enables the software to handle complex arithmetic numbers, to locate complex roots, because we also have complex roots. However, in this class, we will not pursue this idea because, as I said, it's not that important to study complex numbers while we're solving transcendental and algebraic equations. So you can actually find this method very, very easily if you go to literature. But in general, we have a better option for this. So a better option for this method is actually what we call the inverse quadratic interpolation, or the IQI. Okay. So this method is very similar to the generalization of the secant method to parabolas. So it's very, very similar. Okay. However, instead of being in the form of g equal to px, so now we are having actually the opposite. We have the parabola in form of x equal to pg instead of px, which was the assumption of the Mueller's method. One problem in this case is solved immediately. So the parabola that we are proposing will intersect the x-axis in a single point. So there is no ambiguity then to find actually the I plus 3 points, because we are given, of course, 3 initial conditions, but there's no ambiguity, because as long as we intersect the axis in one single point, we just actually can obtain the next point from the previous guesses. So xi, x1, sorry, xi plus 1 and xi plus 2. So in general, this is what we get, the formula for this method. So this is the formula. So we have that the xi plus 3 is going to be equal to xi plus 2. And then we have all these methods, sorry, all these the denominator and numerator. So with r times r minus q times xi plus 2, xi plus 1, plus 1 minus r times s times xi plus 2 minus xi divided by q minus 1, r minus 1, and s minus 1. So we need at least here 2 guesses, 1, 2. So in general, we are saying that we only need to actually intersect the axis in one single point. So if we intersect in one single point, so we can obtain this one using the previous ones points that are actually, sorry, the other points that are actually xi plus 2 and xi plus 1. So there is no problem with that. So we just fix it in general. So with this in mind, if you see actually we have R and we have Q here and we have S as additional values, right? I didn't put it here because it's going to be like a humongous formula, but Q is equal to the function evaluated in xi divided by the function evaluated in I plus 1. R is equal to the function evaluated in I plus 2 divided by xi plus 1, and S is equal to the function evaluated in xi plus 2 divided by x evaluated in the xi value. Okay, so we have to give 3 initial guesses, and the IQI method is another method working by iterations. And we just use the new guess, which is this one, xi plus 3, to replace the oldest xi. So that's what we're gonna do. Once we obtain this one is gonna take place on this one, in xi. So to make it actually more simple, we are going to solve this exercise. So these exercises are the ones that we're solving here. So we already know the answers for these exercises. Okay, so if you remember, we applied for the example number 1, if x equal to x cubic plus x minus 1, and then the initial guesses was xi minus 1, xi plus 1, and xi I plus 2 equal to 1. So to find the root of fx equal to x to this root. Okay, to this equation. So we are going to do some example very similar to what we did in the second method. So I'm going to propose some columns because we have a lot of things to calculate. But in general, you'll see that this is actually very simple. It's very simple calculation. So for the sake of my sanity, I already have solved this exercise, but I'm going to actually move it to this part. So, and I'm just going to copy the columns here. Copy and paste it. So in general, we have the n is equal to the number of iterations. So because I already know that the solution for this one, so I'm proposing 8 iterations. Okay, n is the number of iterations. So we have xi, which is xi is equal to -1, to -1. Then we have 0, which is xi plus 1, and we have xi plus 2, which is equal to 1. Okay, so if you see the formula here, so the formula, this is the function evaluating the xi value. So we just say equal to this one to the power, let me remember how to use this function, yes, plus xi plus 1, right? So then we have the first initial value. Oops, I think I made a mistake. Yeah, this is minus. There you go. So this is minus. So then we have the same formula, but now it's going to be evaluating xi plus 1. So what I just have to do is to actually move it right here. So now it's evaluating xi plus 1. So and then we evaluating xi plus 2, which is actually the same function evaluating this xi plus 2. So if you see, it's actually very simple, and we're having the same solution as the other ones. But additionally, we have to compute Q, R, and S. So we already know that the Q is equal to the fxi divided by fxi plus 1. So it's going to be this one. We also know that R is going to be equal to fxi plus 2 plus 1, sorry, which is this one, divided by fxi plus 1, which is this one. And then we have that S is going to be equal to fxi plus 1 divided by fxi, this one. So if you see, the numbers are exactly the same. So it's 3, -1, and minus 0.333333. Okay? The only thing that we need to calculate now is then, I think I forgot one of this. Yeah, I didn't copy this one. So paste it. We need the new guess, or the new point of reference in the parabola, for the parabola. So this is very straightforward. So the same thing, xi plus 1, right? So, sorry, xi plus 2. That's a mistake. It's d9. Xi plus 2 minus, I'm going to open a parenthesis, is going to be r times, oops, times R minus Q minus Q, right? And then we're going to multiply this times xi plus 2, xi plus 2 minus xi plus 1. Okay, so and then we have plus, we are right here, is going to be 1 minus R times S times, then we have xi plus 2 minus xi plus, sorry, xi minus xi. Yes. Okay. And then we have just to close the first parenthesis. And then this is going to be divided by another parenthesis, Q minus 1, close the parenthesis, and then open times, open parenthesis, R minus 1, then we close the parenthesis and then open it again, times, close the parenthesis, open the parenthesis, S minus 1, close the parenthesis, and then we have to close the big one, right? And then we have this value. So if you see, the same value we have previously here. So as we said, in general, if we go to the slides, so we said that we have the new guess is going to replace the value of xi. So that's pretty much what we're going to do. So this one xi value is going to be replaced by this one. So in general, if you think about it, so these are going to be the same. But why? Because we are forcing the 2 points to be actually what? To be fixed. And the one we're just gonna be varying is actually this one. So once we have this one, I think this is going to be actually done automatically, right? So we see that if we go here, we have only 78 to 18. So, and then because this is already coded as it's going to take the same, the whole number, we just do this, and then we just solve it. And then we have the solution, 0.6233. So it's pretty much the same as the exercise that we did in the previous method. I don't remember if we have the function here. No, we did it in Excel. But in general, that example, let me open Excel just to remind you that that's something that we got. So I do believe I have the second method exercises here somewhere. Example second, right here. This is the exercise number 1. And yes, if you remember, the second method was equal to 0.6x2331. So this is what we got here. So in general, for your assignment, if you think about it, so you will have to decide what the interval that you have to pick, or the neighborhood, to be able to make sure that the solution is there. You can do it just graphically, or you can select it randomly, as you prefer. But you know that this is accumulating knowledge. So you can use actually the graphical representation of the solution, and then you provide a very good approach, or good estimate of the root. Okay, so this is the inverse quadratic interpolation right here. No, not this one, but this one, right? So I'm going to do another example just very quickly, try to actually solve this. So in general, we have to apply the secant method with starting guesses 0, minus 0.1, and then there is no another guess. But I'm going to just show you how we can do this very easily without any complications. Okay, so if I get complications, I'm just gonna, stop the video and do it. Think about it a little bit, and then we can solve it. So let me just arrange this. I'm gonna use consoles because I'm very picky with the exercises. So I'm just gonna make it bigger for you. And so I'm going to put this in bold font. I'm gonna use this is for the iterations. Like actually, just use another 8 iterations. We don't know if we're gonna need more than that. But let's just keep it. So the first one is actually 0. This is gonna be minus 0.1. And let's just consider, for the sake of, things this minus 1, let's just use the same. So let's use actually the same. So it's minus 1, 0, and 1. So let's see what happened. Okay, same thing. So we already know that this is actually equal to, I'm going to make it a little bit easier, faster, sorry. This is the cosinus of this one plus 2 times the sinus of this one plus this one square, right? So that's a function that we have here. So this is the function evaluated cosinus of x plus 2 sinus of x plus b1 square. Sorry, x squared. So we have this one. So if we just do this, so we already know that this is x plus 1 here, which is 0, 0, 0. It's going to be 1, of course. And then we have the xi plus 2 evaluated. So we just need to compute actually q, r, and s. Oops, sorry. Q, R, and x. And I'm going to bring the equation to, again. So I'm going to bring here the equation. So this one. So let's just define q. Again, q is equal to fxi, sorry, divided by fxi plus 1. Yes. Oh, so here we have a problem. So let's actually, instead of actually fixing this as a number equal to 0, let's just use 0.1. So this is something that sometimes happens. Don't worry about this. So we'll see how it goes. So R is equal to fxi2, which is this one, divided by fxi plus 1, right? So you see it, this is fxi plus 2 divided by fxi plus 1. Q is equal to fxi divided by fxi plus 1. And then S is going to be equal to fxi plus 2 divided by fxi. So you got it here. So you got it here, right? This is fxi plus 2 divided by fxi. So, and then we have to just replicate the formula. I'm going to actually try to just copy and paste it. So, in general, this should be fine. This should be okay because we are generally using this. You just I copy all the equations because this is actually very, it's kind of like long equation. I'm assuming that this works because if you see here, the bottom is q minus 1. It's r minus 1, and this is this is s minus 1. So it's fine. And if I check this again, so this one is xi plus 2, sorry, minus r, which is this one, yeah, times r minus q, which is this one, and times the xi plus 2, which is the blue one, minus the xi plus 1, which is point 1, this column, and then you have the other one. So I'm assuming that this is actually correct. So what I have to do then now is it's just to simplify this, or to actually just replace xi plus 3 in the value of xi. So I just need to replicate this estimation. So there we have. So we fixed this one. We have the same thing. So and then we just have to do it like this. And then if I see, so probably this wasn't actually the best to obtain it, right? So if you remember the solution of this function, we just go to the secant. So example secant. So for the cosinus, the solution was minus 0.652. So minus 6592. So in general, probably wasn't actually a very good idea to do it. So probably this is better if we actually do it minus point 0.5. And then this is going to be minus 0.1. So this is what I got here. Well, actually, this could be equal to 1. Yeah, there you go. Yeah, because we have to actually intersect it into different points. So this is going to be equal to this. So, and then we'll see 0.65. So not good. This is exactly the same as this one. This is exactly the same as this one. So it should actually work. Let's just find the best interval to do it. So let's just do this one as 0.1. This is equal to 0.01. And then this is equal to minus 1. Let's just, this is a matter of just find the right confidence. So I'm not sure about this is correct. So minus 1, 0.1, and 1. How much is this one? 0.65. So let's see what happens if we actually extend the iterations. If we just extend it to this one, so it's not what oh, hold on. So this is a matter of the initial conditions. So let's actually see if this works. This is cosinus plus sinus of this one. This is fxi plus 1. This is the one. And then this is xi plus 2. It should be fine. And then q is equal to, I think this is, I think I have a problem here. Yeah, I think I have, yeah, I found a problem. So you see that I'm not even perfect. So sometimes we make mistakes. So if you think about it, it's fxi plus I. So, and this is fxi plus 1. So this one, we have to make sure that we do things properly because sometimes gets confused. So Q now it's fine. Yeah, R, it's now is fxi plus 2, which is the blue one, and then fxi plus 1, which is the red one. Okay. And then we have the S, which is S is equal to what? fxi plus 2 divided in fxi. Okay, so let's see if that works. So I'm assuming that this is fine. So then this is going to be the same, and we hold this one, and let's see what happened. This doesn't make sense because, hold on a second. And then point, this is going to be, okay, so probably 1 minus 1. So 0.5. So let me just, okay, guys. So it took me a while to actually find the roots, but this is actually a very good exercise to give you a good use of the knowledge you had previously acquired. So in general, for example, so what I did is actually I went to MATLAB and I uploaded the function cosinus plus 2 sinus of x squared. So in general, this is, you already saw this one because you have the graphical solution. So, and then I run it. I got this one. I'm just gonna run it. Oops, no, not this one. I'm just gonna run it. And then I got this one. So this is actually very curious case. So if you see this part, so the x-axis is here. So there is no intersection between the x-axis in other points. So for these cases, we have to suppose a very close interval between the solutions. So we already know the solution because we used the secant method previously, and it's minus 0.665927. So it's about 0.6. So, and then we have to suppose in this case, or give initial guesses that are very close to the solution. In general, what I did is just to actually give 0.7, 0.6, 0.5, and then I just, do the same thing. So in general, I'm gonna actually cancel this. I'm gonna delete this for you to see it. So this one is going to be the one that is going to be updated as in the previous exercise. So I'm going to just solve this one for here. Oops. So, but in general, so hold on. I'm gonna solve this one for this one. Okay, and then I'm going to solve this one. So you see here that in general, you see that we have a solution very similar to what we have in the other one. So we just update this column again, similar to what I have here, and then we obtain the solution. If we see the solution here and the solution in the secant method, so the solution is equivalent. It's actually the same thing, 0.65927 negative. So, but in general, this took me a while. Why? Because I found that the function doesn't have intersection very close to the x-axis. So the parabola method is not as convenient in this case. So be aware of this because this is not what you are expecting sometimes. So the exercises could have some tricky knowledge or tricky, like thing to actually be solved. But in general, these are the two examples of the IQ. Well, I'm using the IQ here. So in general, if we want to actually change this, the context, so we have to say to apply the IQI method, which is starting guesses of minus 0.7, minus 0.6, and minus 0.5. But this is actually very tricky because the analysis of the curve doesn't show me that it have intersection with the x-axis. So but I did it. So I did it. It's here. So that's in general how we solve the IQI method. These two examples give me actually two of the good cases to show you how to do it. So in general, if you want to just keep practicing the IQI method, you can do this. You can do the other exercises. These exercises. So this one. So you can do this one, and this one, just to keep practicing. Be aware that you have to give me actually, you have to provide a new and additional guess, but I recommend you to actually plot this one. For example, if I go to cosinus of x plus cosinus, I just have to go and then use MATLAB, and then x plus, right? Plus cosinus of x. I think that's the equation. So that's the equation, x cosinus of x. So I'm going to plot it. It doesn't matter that it's not, So it's here. So you can find, you see that you will have ranges. The intersection is here. So the solution would be about 0.75. You already know this one, but you see that you have two possible roots. So you can actually, give it about here. So be aware of the solution, the range of the solution, to be able to find a good guess for the equation. So that's pretty much, the IQI method. And then finally, we have the branch method. So the branch method actually, it's what we call a hybrid method. So when I say hybrid, it means actually there's a collection of several techniques that we introduced early in the class. And then what, in this case, Brent actually did in 1973. So he used a lot of the methods. In general, he used the bisection method. He used the Newton's method. He used also the IQI. So he uses many of those methods to actually obtain the best and the fastest way to obtain the solution. In general, for example, we are going to apply this in MATLAB. So I'm going to apply this concept. So in MATLAB. So this is the one. So I'm going to clean this up. Well, actually, I'm going to just do it in. No, I'm just going to do it in here. So CLC to clean the board. I'm going to clear also the variables. Clear. CLC again. And then I have the new window. So if I want to actually declare a function, remember that you have the f equal to the at, oops, what happened? Oh my God. I think I closed MATLAB. So sorry, the keyboard, it's very tricky in Spanish. I'm not used to it. I'm getting used to it. So sorry about the conflict. So let's do it again. So f is going to be equal to the at, which is this one, yep, at of x, of course, because it's a function of x. And then I'm going to use the x cubic, then cubic, yeah, plus x minus 1. So that's my function. So it's already, the function is f. So the command to actually solve this in MATLAB, and this is not only, guys, not only to using the branch method. This is a way in general to solve any type of equation you can face in the future in your assignments or in your whatever you prefer. Like you have plenty of courses that you're gonna use a solver. So in general, the function to use is the f0 function. This is the f, that is the equation that we already declared. We have to provide a range. The range is going to be from 0 to 1, which is the bracket. It is the A and B bracket. And then comma, I'm going to give the t m optim set, and I'm going to create or I'm gonna give the options of, oh my goodness, this is complicated because I don't know how to say to do it. Display, comma, and then I have another one that is iteration. So I'm gonna display all the iterations that we need. So in general, I'm gonna click enter. Oops. Oh, I miss a parenthesis. Sorry. I'm gonna click on enter, and then you see here. So in general, this is gives you all the the iterations in here, and then we obtain that the first is x is equal to 1, and then evaluate is in 1, and then the initial is the 1. Then he used the bisection, and then he used the QI interpolation, QI interpolation, QI interpolation, until the fx is equal to 0, which is actually what we wanted, because the fx, this one is equal to 0. And the solution is 0.682328, which is the same solution as we obtained for this original one. So this is also provided here. So initial, it uses the bisection method, and then you use the interpolation, the IQI, the one we did. So let's actually do the example again, this example, to show how it works for this one. So let's just go and then use the same thing here, just declare this example to see that sometimes the computer gets also tricked, but we're gonna solve it. So, oops, let me just use 2 times sinus of x, and then plus x squared. So I think that's pretty much right, the equation. So yep, the fx cosinus of x plus 2 sinus of x plus x squared. So there you go. You have the range. So and then we're just gonna copy the command. Actually, if you just click on the error, so you can get it here. And then I'm gonna say like that my interval is gonna be from -1 to 1. So and because we are using several methods, let's see. So there you go. So first the initial one, and then using the IQI, and then the bisection, and then the IQI, 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 until it gets actually a very low residue, which is -1 to the power -16. So times 10 to the power -16. So that's a very low error. And the solution is 0.659266. So in general, if you see the solution, we got for the example 0.65927, and this is 0.593, pretty much the same. So this is how we use the branch method. So the branch method is actually a combination of several methods. So it's a hybrid, okay? So it provides a fast convergency, of course, because it's not sophisticated because it was actually, like 1973, but it's a good way to actually provide a good verification for your assignments, okay? So that's the way it works. That's what I have here. And then we have the assignment 8. So the assignment 8, this is the one that is going to be posted, and then you will have all your period of vacation to solve these examples. So this is the CON method, the method false position, the IQI method. So then it has a little bit of some of the some tricky and more formulated examples, but it's still the same thing. So, and then you have several ways to do it, and you have to rank it. So rank them for the speed of convergency from the fastest to the slowest. So this is, how many iterations you use for this one, how many iterations for this one, how many iterations for this one, and then, you have to rank it. You have to use all the methods that we already have. So we have the 4 methods. So we have the bisection, the second method, the fixed point iteration. So, and then you can say like, are there any methods that will converge faster than all above suggestions? Probably if you use the Newton's-Raphson method, it's actually better. But I don't know. This is just an example. The equations are very simple, are straightforward. They are actually algebraic. So you don't have to do a lot of things. So of course, there are some other exercises like use the secant method to find a single solution for the equation in exercise 1. This is the exercise 1. So you have multiple equations. Then use the false position. You can actually do it again. And then the quadratic interpolation for the exercise number 1. So this is what you have here. So this is exactly what I'm asking you to do. And you will have it this already, you will have actually this posted in Eminus for further information. And then remember, if you don't find the root, you have several ways to actually help you out. You know, you can use the graphical method, you can use other things to help you. So that's important to remember, okay? That's it for the root finding without derivative. We are done with the methods for transcendental algebraic equations. So we're moving forward to system of equations. And that's it. So have an excellent dead week or holidays. I'll see you later. And I hope this video is clear enough to actually do the IQI method and the others examples. So I'm looking forward to meet you in 2 weeks. Have fun. Peace out.